A natural extension of the transformation of probability density functions is the moment generating function. Actually, with the moment generating function, we should be able to determine the distributions of the sum of different random variables. So what is a moment generating function? First of all, what is a moment? The moment is concept is very simple. Actually, expected value of x to the power k is the kth moment of the random variable x. So basically, when k is equal to 0, we have expected value of x to the power 0, which is going to be equal to 1. When k is equal to 1, which is when we are going to have expected value of x, what we call population mean. When k is equal to 2, maybe at this point things start to be a little bit more interesting. Expected x square is going to be our second moment, and note that is going to be equal to population mean and population variance squared together, or the distribution mean and the variance of the distribution. So you can go by this way to the higher moments. So what's a moment generating function? A moment generating function represented with moment generating function of the random variable x is actually a function of t, and is simply expected value of exponential t times x. So basically the meaning is we multiply the random variable x by a parameter, a constant t, and we take the exponential of that term and we find the expected value. Now you may ask, why do we bother with such a complication, taking the expected value? Note that when we have some, usually in mathematics or in physics, when you have an exponential function, usually that exponential function helps in changing an additive function, a multiplicative function, into an additive function. So what do I mean by that? For instance, exponential a times exponential b is actually equal to exponential a plus b, which is something that we all know from high school. But what is interesting is actually, as you are going to see in a series of random variables, when we would like to add these random variables, actually that means actually that operation here would correspond to the product of two exponentials. So we may use that property here. So, but until reaching to that step, we need to cover a couple of more steps here. So this is the moment generating function of x. Now the important property of moment generating function of x is, if you take the kth derivative with respect to t of the moment generating function of x and evaluate at t is equal to 0, what you obtain is exponential x to the power k. You may say, where did that come from? Actually, it's very simple. When we take this, let's prove this. Actually, let me prove this for k is equal to 1. Instead of this one, we are going to write exponential tx, right? Since actually this derivative is and exponential are linear operators, we can write this as expected value of dtx dt, which is going to be equal to, now with respect to t, and note that these are going to be at t is equal to 0. Let's not forget these. All right, when we take the derivative with respect to t, it's going to be equal to expected value of x times exponential tx evaluated at t is equal to 0. When you put t is equal to 0, you have exponential x here. So if you just use this for different values of k, higher orders, you are going to obtain this result. In another way, which makes, I think, this whole thing slightly gives a general vision. Now, the exponent here, if you write the Taylor series expansion here of exponential tx, if we write the Taylor series expansion, it's going to be like this. And it's going to go to, let's write an intermediate k term here, k factorial x to the power k, and this is the the Taylor series expansion of exponential tx. Now, expected value of exponential tx is going to be equal to, now note that again t is the constant value here, so x is the random variable here, so it's going to be equal to 1 plus t exponential x plus t square over 2 exponential x square plus it goes t to the power k factorial exponential. Now, this means that is a very nice property, as you can see. Now, each expected value of each moment, so this is the first moment of x. Actually, you can see here, take this as 1 times 1. So this is the 0th moment of x. This is the second moment of x. So these here coefficients here, note that these coefficients, actually exponential, the expected value of exponential tx will be a Taylor series expansion, which is going to be a coefficient, which is a function of t multiplied by the moment of x. So when you take the kth derivative of this, let's put it here, see. So what we do is we take the kth derivative here of this function evaluated t is equal to 0, which is actually this function, exponential tx, evaluate at t is equal to 0. So what we obtain here is, you take the derivative, for instance, when you take the first derivative here, we are going to end up with exponential x plus other terms, but there is going to be some t terms left here. So when you put t is equal to 0, all the other terms will be equal to 0. Therefore, we are going to have, when k is equal to 1, we are going to have this is going to be equal to, let me put it that way, it's equal to exponential x when k is equal to 1. Maybe it's easier to see in this fashion. So when you take the derivatives 2 times, this part will disappear, because once you take the derivative, there's going to be a constant here. Take another derivative of t is going to be 0. So when you take the derivative twice here, it's going to be 2t and then 2 over 2, which is going to be exponential x squared plus some terms, but they are going to be always the coefficients that contain t. So when you put 0 here, they are going to cancel. So we are going to have exponential x squared when k is equal to, so it goes like this. So this is another way of showing how the moment generating, the derivative, kth derivative of the moment generating function is actually equal to the moment, kth moment of that random variable. Now let's use this on a couple of examples before achieving our ultimate aim for using these moment generating functions, which is actually to find the distribution of sum of different random variables. But before that, I should mention another thing. Without proof, there is one-to-one correspondence between, so let's write it that way. If the moment generating function exists, then, because it's possible that it may not exist, then there is one-to-one correspondence between the moment generating function and the probability density function or probability distribution of x. Now that's an important thing, which means that if, for instance, your moment generating function is a certain form, for the different distributions, we are going to find different moment generating functions. Once you have the moment generating function, you can always go back to the distribution. Not only the moment generating function is unique, but it also gives the whole information about the probability density or the probability distribution function. And more importantly, it is unique. So you can always go back to the probability distribution. And that's going to be an important property here, because what we are going to do is we are going to change the probability density function. We are going to transform it to the domain of moment generating function. Then we are going to do calculations here. And then we are going to see that we can back transform it to the probability density function domain, if that is the correct phrase. Anyway, let me try to solve a couple of examples here. First of all, a binomial distribution. For instance, let's say that x is binomial distributed with n number of trials, and the p is the probability of success here. In this case, I would like to determine the moment generating function of that random variable. So it's going to be what is mxt? Actually, the idea is very simple. We are just going to take this and put it into this form here. So the expected value of, let me write it that way, expected value of tx is going to be equal to expected value tx multiplied by fx here, and x is going to be from 0 to n, because here x will be from 0, 1 to n. This is the domain of x. So therefore, and this is a discrete random variable, therefore it's going to be equal to x is equal to 0 to n exponential tx. Instead of that, n choose k, probability over p to the power x, and 1 minus p to the power n minus x. Okay, now this term and this term is the common power x here, so we can write it as from x0 to n and x, and we are going to have let's see, exponential t p x here, as you can see, times 1 minus p n minus x. Now you should realize that this is actually equal to exponential t p plus 1 minus p to the power n. This is the expansion of that term. Each term is going to have this coefficient here, and choose k, and each of these terms here will be raised to the power starting from this n is going to be n minus 1, n minus 2, and it's going to be starting from 1. It's going to increase its orders. Now this is the moment generating function of binomial distributed random variable. Let's show that this is indeed the case. So remember that the expected value of a binomial random variable is n times p, and the variance of a binomial random variable is n times p times 1 minus p. But actually, let's convert this to expected value of x squared, which is the second moment of the binomial distributed random variable. This is going to be equal to this quantity plus this quantity. So it's going to be variance x plus expected square. So this is going to be equal to n squared p squared plus np minus np squared. So in common parentheses of n times p, it's going to be equal to 1 minus p plus np. So this is the result that we have. We know just using our previous knowledge about the distributions. So just from the distribution, in the distribution domain, I may say, using the properties of the distributions, we can find the expected value and the first and the second moment of x. Now, using this moment generating function, this says that expected value of x should be equal to the first derivative here of that moment generating function at t is equal to 0. So we are going to take the derivative with respect to t here. So let's do that. It's going to be p times exponential t. It's going to be p times exponential t here. And we are going to have an n term here. So it's going to be a t plus 1 minus p and minus p. This is going to be evaluated at 0. Note that this is the derivative of that term here is going to be and the very same term, and here we have p times exponential t. So when you put t is equal to 0 here, note that this is going to be equal to, when you put, it's going to be 1, p minus p will be 0, so it's going to be 1 here, and p e to the power 0, so this is going to be another 1, so we have n times p here, and we have the first check. And when we have exponential expected value of x squared, we are going to have the second derivative here. T is equal to 0. So we can use this one and take another derivative. So if we take this as the constant term here first and take the derivative of this once more, it's going to be n minus 1 exponential dp p plus 1 minus 1 n minus 1. Let's see, plus taking this term as the constant, this is going to be equal to n times p exponential t e t p plus n minus 1 evaluated at t is equal to 0. All right, let's see. When we put t is equal to 0, note that as we have calculated here, this one and this one is going to be equal to 1. So we have here what? Another one here and another one here. And we have another one here. Therefore, we are going to have n times p times square n minus 1 here plus np. Let's make it look nicer. Take into the common parenthesis np is going to be equal to 1 plus np minus p. And let's see, it's going to be np1 plus np. Yeah, as you can see, these also check. Well, although, as you can see, the original method seems to be easier, in some cases, it may be such that, well, for instance, variance of x may be difficult to find, or expected value of x may be difficult to find, and it may be much more easier to determine the expected value of exponential xt. So in those cases, this method may easily be used. Let's continue this on another example. For instance, for Poisson distribution. So for Poisson distribution, our probability mass function is equal to, let's only talk about, take the capital T, the time interval to be equal to 1 to make life easier for us. So we are going to have exponential minus lambda, lambda to the power x factorial. So we have x from 0, 1 to plus infinity. So what we are interested in here is to find the expected value of x, and we know already that this is equal to lambda. So let's prove that this is the case. So what we are going to do is to find expected value of tx and take the derivative and evaluate it at t is equal to 0. So the expected value of tx is going to be equal to tx exponential minus lambda x factorial from x0 to infinity. Let's see, we have, this is in terms of x here, and this is lambda. Well, it can be easily, I don't like my writing. So this term can be taken out, exponential minus lambda, and we have here exponential t lambda to the power x divided by x. Yeah, this is also an x. And this is x from 0 to infinity. Note that this is actually let's see, x to the power x. So this is a power series, like right. So therefore, this is going to be it's going to go from 1 to lambda exponential t over 1 plus lambda exponential t over 2 plus it goes. Therefore, this is going to be equal to, this part is going to be equal to exponential lambda exponential t. So when we multiply this by, okay, this part's going to be this one. So when you multiply this term by this exponential, we add these terms, it's going to be equal to, in common parenthesis of lambda, is going to be exponential t minus 1. Therefore, this is going to be our moment generating function for the Poisson distributed random variable. Now we need to take the first derivative of this, right, and evaluate at t is equal to 0 to determine the expected value of x. Let's do that. Well, actually, this exponential times x power exponential thing is a little bit tricky for me, so I'm going to write this as exponential lambda u, where u is equal to exponential t minus 1. Therefore, the derivative here is going to be dm over du over dt, evaluated at t is equal to 0. So let's do that. dm over du here, since now we have here as our m, is going to be equal to lambda exponential lambda u. Now instead of u, I'm going to be writing exponential t minus 1 du over dt is going to be equal to here simply exponential to the power t, which is evaluated at t is equal to 0. When we put here 0, this is going to be equal to 1. When we put here 0, this is going to be equal to 1. Here's 1 minus 1, 0. So this whole thing is going to be equal to 1. So we obtain lambda. Now let's solve another question. This time, let's find the moment generating function of a Gaussian distributed random variable. So what we are simply going to do is determine this for Gaussian distribution, which is a bit more going to be a bit more involved, but not too much. So it's going to be from minus infinity to plus infinity, 1 over 2 pi sigma square 1 over 2 exponential minus 1 over 2x minus mu sigma square. This is our probability density function. This is going to multiply by exponential tx and integrated by x. So we can take the constants out. 1 over 2, and it's going to be 1. And here inside the integral, we are going to have 1 over 2. Let's write this term by term minus x squared minus 2x plus m squared divided by sigma squared plus tx dx from minus infinity to plus infinity. So what I'm going to do is, let me actually multiply these both sides by t square x to make it look nicer. Now there is, as you can see, an x term here and an x term here. We can do something called completing the squares, or completing the square, which is basically what I'm going to do is I'm going to determine here a squared expression, a sum of two terms squared, and I'm going to subtract the additional term. So what I'm going to do is this. Oh, by the way, I think I made a mistake here. This should be minus, because we have already a minus sign here. So I should be careful about this. So I'm going to only concentrate on this part, and I'm going to complete the square of this part. So here, this is going to be x squared minus 2 mu plus all right, plus mu square. This is the term at hand here. Now this term is basically equal to x minus this whole thing here. Oh. So this part is going to be up, if I can draw it, which I see. Yeah, okay. So it's going to be 2 pi, if they take the constants out, sigma here, plus infinity, exponential minus x squared minus 2mx plus m squared. I should be very careful with the signs here. Actually, I have a 2 here, so let's put it into minus 1 over 2. And we got plus tx here, dx. Now I'm going to concentrate only on this part. So this part is going to be equal to minus 1 over 2 x squared minus 2x plus mu squared. This part is going to be, if I multiply this by 2 sigma squared tx, it's going to be here divided by sigma squared. Now that's nice. Now I'm going to concentrate only on this part. Then I'm going to handle this minus 1 over 2 sigma squared. So it's going to be equal to x squared. We have, let me write it that way. We have minus 1 over 2 here. So I made a crucial mistake. This should be a minus sign here. Yeah, because we got the common minus 1 over 2 here. So this should be also minus. X squared minus 2 mu plus, let's also keep 2 out, 2 mu plus sigma square Tx, all right, plus mu square. Now this can be, completing the square comes into play here. I can write this as a square of these. Note that these first two terms, x squared, will come from here, and this term is going to 2 times x times mu plus sigma square T will form these two terms. But additionally, there is going to be another term. What is that term? It's going to be actually equal to square of this term here. So the square of this term, this is going to be subtracted here, which is going to be mu square and plus 2 mu sigma square T and sigma to the power 4 T square. And we have also mu square here. So these terms, right, will correspond to those first two terms here, right? And there's going to be additional mu. What I'm going to do is I'm going to place these terms into our exponential, and let's see what we are going to obtain. So we had the term here 2 pi 1 over 2 sigma, and we are going to have our exponential here, exponential minus 1 over 2, this term here, x minus mu plus sigma squared T divided by sigma square, and all these terms are squared. And we are going to have also this other exponential term. Actually, note that these mu squares will cancel and these don't have any x terms, so I can write it as a, and I can take that exponential. I will take that exponential. So it's going to be again 1 over 2 minus 1 over 2 with another minus sign. So this is going to be just plus 2 mu sigma squared T plus sigma to the power 4 T squared. But we are going to have also this term here. Note that we have not included these terms in our derivation. Now I include them here. Let me make it look nicer. This part is going to be equal to 2's will cancel, sigma square will cancel. It's going to be mu plus and sigma to the power 2 T square over 2 in exponential. And I can take this term out because it doesn't have any x terms. So take this outside of the integral, and it's going to be exponential mu plus sigma square T square over 2 divided by 2 pi 1 over 2 sigma minus the very same term here. Now at this point, this actually is a Gaussian integral. So let's make it exactly look like the standardized form that we have solved previously. So what I'm going to do is I'm going to call z to be equal to x minus mu plus sigma square T divided by standard deviation. So this is going to be equal to dz times standard deviation is going to be equal to dx. So I'm going to replace the dx here, which I forgot to write here, with dz, this term. So this is going to be actually, let me write it here for sigma times dz times exponential minus 1 over 2 z squared. Now these will cancel, and now when we put here this term inside here, this whole expression will be equal to the Gaussian integral, and it's going to be equal to 0. And now we have found, with a little bit more labor compared to the other two questions I tried to solve, this is the moment generating function of the Gaussian distributed random variable. So here note that this is mu. All right, now let's show that this is indeed moment generating function. So what we do here is we are going to take, have I missed anything? Let me see. Yes, I have missed a t here. I realized there is a t here, which I missed, and it's very important. So we have one t here. So the final form is with the t here. Let me write it clearly. Exponential mu times t plus sigma square t square over, let me write it that way. So that t, yeah, this is our moment generating function. Now, if I take the first derivative of this moment generating function at t is equal to 0, note that it's going to be equal to mu plus 2 sigma t over 2 times this exponential moment generating function itself. These are evaluated at 0. Now, when we evaluate this at 0, 0 and 0 is going to be 1. And there's another 0 here. So we have found this to be equal to mu. And when it comes to the second derivative of the moment generating function evaluated at t is equal to 0, well, okay, it's going to take a little bit more time. So let's see, we have here the first derivative is this one. So this is going to be simply equal to mu plus 2 sigma t over 2. And we are going to have another mu coming here. So we are going to mu x t. And then considering that this time this is constant, it's going to be 2 sigma square over 2 mu x t evaluated t is equal to 0. These will cancel. These are going to be equal to 1 here. This is going to cancel. So this is going to be mu square plus sigma square, which is the result that we need to find actually. So the second moment is equal to distribution mean squared plus variance. Okay, now what did I solve for 3 different systems. I solved these questions. Shall I also solve it for gamma distribution? Well, let me also solve it for gamma distribution. Then I think that would be sufficient. Then I'm going to continue with summing the random variables. Now for gamma distribution, expected value of xt is going to be equal to, for gamma distribution, we are going to have here a, and we are going to have here, actually it's going to be like this, call it a, and this b to the power a, and we are going to have x to the power a minus 1 and exponential minus bx. This is the form of the gamma distribution, and we are going to multiply it by exponential xt, and we integrate it from 0 to infinity. So what we are going to have here is b to the power a. We are going to have exponential a minus 1, exponential b, let me write it that way, exponential b minus tx dx. Now note that this and this is going to be 0 to infinity. This is going to be our b prime here. So when you integrate this function here, what we are going to obtain will be actually equal to, this part will be equal to a divided by b prime to the power a. So when you multiply those two, the result is going to be equal to b over b prime to the power a. And now let's write the values here. B prime is b over b prime is equal to b minus t to the power a. And hopefully gamma distribution, although probably this seemed like the probably most complicated of distributions, actually it is very easy to derive the moment generating function of the gamma distributed random variable. Now, how can we use this moment generating functions? Let's start with a very simple example. Let's say that we have 2 binomial processes. So actually corresponding to the binomial process example, maybe I can show it on the right hand side, which is going to make the, yeah. Since I have already derived here, I may continue, for instance, for this part. Let's say that we have 2 binomial random variables. And with the same identical p-values, but with 2 different number of trials. So you may think about, let's say you solve a test question with 4 multiple choice test question, and you're gonna have no idea about the answers. You first solve 10 questions, then you solve 20 questions. So what you are interested in is, for instance, this function. Y is equal to x1 plus x2. What is the distribution of y? Okay, so the idea is pretty much simple. Exponential y if you write the moment generating function for y, and if I can, yes, this is going to be equal to expected value of exponential yt. Now, instead of y, I can write x1 plus x2. So it's going to be x1 plus x2t. It's going to be equal to expected value of x1t times expected value x2t. Now, here is the very important point. If x1 and x2 are independent, then this can be written as expected value of x1t times expected value of exponential x2t, which means this is going to be equal to moment generating function for x1 times moment generating function x2. So here is the idea. If we do this computation, if we find the moment generating function of x1 and x2, and if we take a product of those, note that you can generalize for any number of independent binomial distributed random, or actually any distribution random variables, but here we are specifically talking about binomial distributed. This is going to be equal to the moment generating function of t. So you may say that what am I going to do with that? But note that since there is one-to-one correspondence between moment generating function and distribution function, we can go back to the distribution function here. So basically, let's see what was the result that we have found in moment generating function for binomial distributed random variable. Yeah, that was the result. So for mx1 is going to be equal to all these results with n1. So this is going to be, let me write it, for mx1, we are going to have etp plus 1 minus p to the power n1. And mx2t is going to be equal to, with the very same expression, raised to the power n2. So what we do is we would like to add those two random variables. In terms of moment generating function, it means multiplication. So when you multiply those two, what you obtain at the end will be like this, n1 plus n2. So this is going to be the moment generating function of t. Now, from this part, how can we go back to the distribution? Very easy. Note that this form is exactly the resulting form. Think about this as a new n, call it n. This is the moment generating function of a binomial distributed random variable. Therefore, now y would be binomial distributed with n trials, and here I can write n, which is equal to capital N1 plus N2 with p degrees of freedom. So very simple. So let's use it for what did we have here? Okay, Poisson distributed random variables. So we have two Poisson distributed random variable, x1 and x2. We are interested in the summation of these. Okay, let's make it something like this. Let's say that we have an office here and we have another office here, right? And these are, let's say, the same time intervals, or any time interval that you take, it doesn't matter. But within that time interval, we have a lambda1 and lambda2 corresponding Poisson rate parameters. Let's say that there is more calls to this office and there are less calls to this office. So what we are interested in here, if the number of calls to that office and to that office are x1 and x2, what is the distribution of the total number of calls? So that's basically our random variable here. So what we are going to do is simply use this equation here. So mx1 is going to be equal to exponential lambda1 exponential t minus 1. I cannot write. Yeah, mx2t is exponential lambda2 exponential t minus 1. And when we multiply those two, it's going to be noted equal to lambda plus lambda2 et minus 1. So this is the moment generating function for the random variable y. And note that if you call this a lambda prime, this is exponential lambda prime exponential t minus 1. Note that this form is identical to the moment generating function of the Poisson random variable. Therefore, y is going to be Poisson distributed with lambda prime, which is equal to lambda 1 plus lambda 2 rate parameters. And that's an interesting thing. If the rate here is equal to, I don't know, 2 hours, two calls per hours, and here, let's say 5 calls per hours, then the Poisson rate parameter of the summation of the total number of calls will be 7 calls per hour. And then what did we have? We had normal distribution. Now let's again solve the very same question. When you have two normal distributed variables, when you add down, what's going to happen? Let's see, where is the thing that we have found? Oh, here it is. So let's say that x1 and x2, let's say that they have the same distribution. Or maybe, okay, they have different distributions. They are both Gaussian distributed, but they have different population mean and variance values. So here, mu x1 is going to be exponential mu1 t plus sigma square t square 2, and x2 is going to be exponential mu2 t sigma square 1 and 2t over 2. So when you multiply those two, we are going to be adding the exponentials, mu1 plus mu2 t plus sigma 1 square sigma 2 square t square over 2. And note that this moment generating function found for y again obeys the same form that we have determined for normal distribution, with the new population mean or distribution mean is equal to mu, and with the new distribution variance sigma square. And we know that actually if we add those two independent Gaussian distributed random variables, mu y is going to be equal to mu x1 plus mu x2, and variance of y is going to be equal to variance of x1 plus variance of x2. Note that the covariance terms will be equal to 0 since they are independent. This is exactly what we have found here. Now, as a last example, it's about gamma distribution. Now, let me do the same thing for exponential distribution. Actually, I have not derived the moment generating function for exponential distribution. So first, let's derive it. Expected value of expected xt is equal to, from 0 to infinity, expected value of xt lambda exponential minus lambda x dx. So we can take the lambda out, from 0 to infinity exponential in minus lambda minus tx dx. So this part is going to be equal to, let's see, minus 1 over lambda minus t, right, exponential minus lambda tx from 0 to infinity, infinity 0. This is going to be lambda over lambda minus t, the moment generating function for exponential distributed random variables. Now, if you have two exponential distributed random variables, then you would like to add them. So what we are going to do is, very simply, we are going to be writing these for x1 is going to be the moment generating function for x1 is going to be equal to lambda minus t. And let's consider the same lambda value here. So we are talking about the same process. So what we are interested here is actually an interesting problem which I have not covered in the lecture, which is related to the Erlang distribution. We are interested in the distance until the second occurrence of that event. So this is the first occurrence, this is the second occurrence. So this is the distribution of y here. Anyway, and mx2t is going to be lambda minus t here. When you take the product, it's going to be equal to lambda minus t is going to be square. Now note that this is not of this form. Therefore, y will not be exponential distributed. Do we have anything here that looks like this form? Yes, as you can see, this is the form that we are going to have here. If you take here b to be equal to lambda and a to be equal to here for 2, then you are going to have gamma distribution. Therefore, here y will be gamma distributed with parameters A to be equal to 2 and B to be equal to lambda. So that's, I think, the easiest way to determine the some addition of different random variables.